Okay. So we're a few minutes, it's about a minute or two past 2 o'clock, so it's probably a good time to start. And the people coming in here late kind of slowed down, so hopefully this is good. So I don't know, I think a bunch of you, but not everyone was here on my Tuesday talk. So this is a series of 2 talks on strategies and challenges of noise reduction and removal. And on Tuesday, I focused sort of on the general framing of the issue and on noise reduction and removal during acquisition. Today, I'm going to focus more on noise removal during, once you have your data, the different approaches people use. And, as I've been staring at this title a bunch of times, I realized that, this might be my own pessimism talking, but the word removal is probably not even needed in this case, because really the best thing we can do is hope to try and reduce our noise sources. And I think both the frustrating and exciting part of this being sort of in the fMRI world is there is no solution. There is no perfect way to remove noise, which means that there's always new problems that are discovered with the methods we are using and new developments that get this thing better. So it makes this actually what could be a dry topic, and probably is a dry topic to some of you, actually has sort of a lot of evolution over the last, many years of fMRI research. Oh, one other thing I'll add, I said this on Tuesday as well. I can drone here for an hour, but it's much more fun to actually answer questions people have than kind of trying to guess what you want to know. So if you have questions, please interrupt. This is being recorded and posted online later. So either pick up the microphone at the front, in that front chair, turn it on and talk through that, or I'll try and repeat questions. But yes, please interrupt. I'd rather not finish because people are excited about stuff than get to the last slide just because I made a last slide. So to sort of go back to the general framework that I presented on Tuesday, there's a lot of definitions for noise, but I think sort of a good general colloquial definition is just the stuff that gets in the way of measuring what you want to measure. And what I like about this sort of, this definition is it's extremely nonspecific. There's what we call noise and what we call signal really depends on what your study's goals are. So, and depending on, and literally in one study's goal, what's noise in one study could be the signal you're looking for in another. So that's one of the fundamental challenges of noise removal is there's some sources of noise that everyone agrees on, yeah, we wish we didn't have that. And there are other sources of noise that are a major issue for one study and a minor issue or a non-issue for another study. So figuring out both what you want to reduce and what you care most about is really study specific. Again, from my talk on Tuesday, I just want to sort of give a general framework of different parts of the fMRI signal from a noise perspective. So in this case, let's imagine we have 2 imaginary time series from fMRI. And these 2 time series are perfectly identical except for scaling. So the correlation between them is 1. And that's called these sort of neural activity. And then we have another imaginary time series that is completely uncorrelated. So when this one goes down, the other one goes up. So there's really, it's not one down, not anti-correlated, it's actually uncorrelated. So there's really no relationship between the ups and downs between these time series. And this is kind of, we want to sort of get to the true neural fluctuations, but there's a lot of other stuff in the data. So there's scanner-based noise. A lot of it is just completely random. There's also noise from signals like your pulse rate and your breathing patterns. So I didn't completely cover this on Tuesday, but those noise sources have 2 origins. One is physical motion. So when your chest is moving up and down, you're actually distorting the magnetic field a bit, and that will, even if your head is keeping still, it could manifest itself as sort of slight distortions or slight motion in the image. And it might not even be enough motion to see like with motion correction, but it does cause these very small distortions depending on the pulse sequence you use. And the other source is you're pushing around oxygenated and deoxygenated blood with every breath and every pulse. And when we're using a method that is sensitive to how much oxy or deoxy blood is in every location of the brain, that pulsation is going to cause signal changes everywhere. And those signal changes are going to be bigger wherever you have more blood. So large arteries, large veins are going to show that, but it's everywhere because your blood is pulsing everywhere. We also have noise from things like head motion. So this could be subtle or it could be large. So let's say you have a voxel, one location in the brain, and they move their head, and that voxel suddenly goes from inside the brain to outside the brain. You're going to suddenly get a very large signal drop. On the opposite side, if you have a location that when they move their head, that we're measuring a signal that was outside the brain and goes inside the brain, or it's changing from gray matter to white matter, which have different signal properties, or gray matter to the cerebral spinal fluid, you could see a signal increase as it moves around. So this is going to cause fluctuations in the time series based on how you move your head. There's other things head motion does, like spin histories and other stuff, but I think that's too much detail for right now. If you put this all together, we get these, you have the original signal that we want to measure, we got scanner noise, we got respiration, we got motion, and then these two time series that were originally identical are still highly correlated, but not quite as strongly. And two time series that were not correlated at all, you add this common signal like the cardiac noise and the pulsation, and suddenly you have a correlation that could be significant. And again, this was for my talk on Tuesday, but as a reminder, how important this is varies. So if we're doing a model-based fMRI study where we're showing someone stimuli and saying what's happening in on versus off, then the fact that two time series are correlated doesn't really matter because we really care about how a signal increases with task and decreases when task is off. So as long as that respiration and cardiac and motion isn't correlated to your task, you don't have to worry. But if we're doing connectivity-based, where these correlation values actually are a result of interest, then this could be very damaging if we don't remove noise. So, like I said, on Tuesday was focusing mostly on acquisition. Today I'm going to say we got our data, we did our best to reduce noise in the acquisition phase. How do we deal with noise here? So I've divided this into four topics. So to decide how to define signal and noise for a study. I've sort of glancingly covered that in both lectures, and I'll be covering in both lectures. There's reducing noise and acquisition, that was last lecture. And the two main topics I'm going to be covering today are removing noise from the data and avoiding analyses that are sensitive to bias noise. And I'll only lightly cover that last one, but I think it's something that is under-acknowledged in that there's a lot of decisions we make in analyses where we enter a study saying, I want to I want to see this result using this method as opposed to what method is most robust to the result I'm doing. So sometimes it would be better to change your goals if you're going into it knowing there's an artifact. I'm going to divide this talk into three philosophies of this post-processing noise reduction methods. And the reason I'm calling it philosophies is these aren't each of these categories isn't necessarily specific methods. It's ways of thinking about how we want to remove noise with fMRI. The first category is what do we think our data should look like? So I'll obviously go into this in a bit more detail, but the idea here is you have your fMRI data, you don't know anything else in the world, but you look at the data and you say, in some way you're saying, that looks like signal, that looks like noise, based purely on the data, and you're trying to make assumptions on what is good and what is bad and remove that. And as a broad overview critique, with my title of the least bad ways to remove noise, these methods are all limited by our assumptions. So at a fundamental level, we're looking at data saying, this is what I think a noise should look like, and these methods are only as accurate as those assumptions are true. The second general philosophy is, removing noise based on external measures. And the fundamental limit of these methods is they depend on how accurately those measures are. So this is stuff like you're measuring pulsation, you're measuring respiration directly. And we can use that data and it gives more validation, but we have to find a way to connect those back to noise in the actual data. And the third category I'm calling based on the physical properties of the data. So we based on the physics of the signal, we know what a blood oxygen weighted signal should look like and what other signals shouldn't look like. And there's a couple of methods, I'll focus on one here, that sort of use these physical properties to remove noise. And the limit to these methods is that they depend on what the physical properties are. So if we're removing data that is not bold weighted, so blood oxygen weighted, that removes a lot of noise, but there's noise that is blood oxygen weighted, like respiration volume changes. Like respiration changes when you take a deep breath, you're changing your blood oxygenation. So these methods in isolation would never remove something like that, even though they can be quite powerful. And the last thing I want to focus on here is, like I said at the beginning of the slide, these are philosophies. These aren't methods. And pretty much every method I'm showing you in practice, sorry, that's popping on my screen. Every method here I'm showing you on practice is, in some form, it's going to be a combination of these. So each method, I think, fits well into one of these three categories. But as you'll see, they do blend a little bit. So before I jump into the first one, any questions so far? OK. So the first one is removing what we think is noise. And I'm going to start with the most obvious case, which I think has been around for noise removal since either since the very beginning of fMRI or almost the very beginning of fMRI, which is removing the slow signal drift. If you put someone in an MRI scanner and you start collecting, actually, if you put a jar of oil in an MRI scanner and you start collecting data, and let's say you collect 5 or 10 minutes of data, your signal will slowly drift. So at any given location, the signal will slowly get a little bit, you'll kind of see like the noise bouncing up and down, but the signal will either slowly get larger, slowly get smaller. It might be a straight line, it might have a little bit of a curve to it, but you always see this. And there's several reasons this could happen. One of them is limits to the scanner hardware. Others are just essentially as the scanner heats up a bit, it could be responsible for some of that drift. But it's a physical issue with the scanner that causes this signal drift. So pretty much from the early days of fMRI, can I say back before most of you were born? Yeah, I think I can say that. Feels weird, but yes. Yeah, okay, I'm feeling old suddenly. So the general approach to this was you say, we know there's this drift, we know it's not actual bold weighted fMRI, let's just regress it out. So here's an example from a recent paper that actually focuses on, this paper is focused on actually removing this drift for real-time analysis, but it has a nice image of this. You're doing some sort of block design task where you have rest, you have task, the signal goes up, you have rest, you have task. And you can see that over time, in addition to this block, this activity we're seeing, the signal slowly drifts up. So you literally can just regress out that slow drift and say, we know that's not real, we know that's not part of the brain, we can just remove it. And the reason I'm starting with this here is because it's both really obvious and makes a lot of sense, and it's not quite as obvious as we'd like to think. Because we also know that the brain changes slowly over time. From the neuroscience perspective, the two examples of where we care about slow signal changes are learning studies. So you're presenting someone, some task over time, we're supposed to be learning and getting better, and we don't expect, a block where they're learning and a block where they're not learning. We expect sort of something to slowly reorganize over time. And also drug studies. So you want to see what the effect of a pharmaceutical compound is on the brain, and you put it in, and there's going to be a response that's, as the drug enters the brain, we expect to see a slow response. So these are slow neural changes, and if we just regress the signal out, we lose that information. So as an example of how this can be, shown in practice, Jen Evans, who's at NIH, designed this study, which isn't a pharmaceutical study, but it sort of models what we would think of as a drug study, where she put people in the scanner and showed a very high contrast flashing checkerboard. And slowly over the course of 3 minutes, that high contrast flashing checkerboard, the contrast decreased and decreased and decreased until it was off. So, and usually something over 3 minutes, that's going to be signal drift. So if we just look at that data as raw data, you don't really see much here. It's just kind of flat. But if you use a method that I'll discuss a little bit later called multi-echo fMRI that can potentially separate scanner-weighted linear drifts from blood oxygen-weighted drifts, what you could see is after this noise removal process, we actually see this pattern. The signal goes up and slowly returns to a baseline, and it separates that, in this case, from a drift that was based on just sort of the scanner noise that went in the other direction. So this is an example that might not come up in people's lives day to day, but I think it was a good place to start to sort of show that even something as simple as scanner drift is worth more thought when we're talking about noise removal. Okay. The next example I'm going to talk about is something that is near and dear and pain to my heart, which is called global signal regression. And the reason I say that is because people here have been arguing and debating people at other universities for way too long on whether this is a good or bad analysis step. And I'm going to frame it here less on good and bad and more about how to think about noise and how we remove noise. The example of global signal correction originally started in one of the first major resting state papers. So what these authors did is they collected fMRI when people weren't doing anything, and they said what correlates to the posterior cingulate. And when they looked at that correlation, they saw that there was one network of areas that were positively correlated with that, these reddish areas, and a whole other network of areas that were negatively correlated. And they built an exciting model of overarching theory of brain function that the brain is intrinsically organized into these two anti-correlated functional networks. So even when you're not doing a task, when one of them is positive, the other is negative, and when the other is positive, or vice versa. And this red area was the area I mentioned on Tuesday called the default mode network. So these are the areas that when you're not doing tasks get bigger, when you are doing tasks, which are the blue areas, it flips. So it was a big, beautiful theory. It got a lot of attention. I'm not calling it right or wrong because the evidence actually is kind of complex here, but it got a lot of attention, and it really jump-started the whole idea of using resting state and resting connectivity. The trouble is, actually, I didn't mention the most obvious thing here, what I mean by global signal regression. So by global signal regression, what that means is you take an average of every voxel in the brain. So you get one average signal, and you remove from every voxel's time series anything that correlates with that average signal. And the concept behind that is brain activity isn't global. You have many different areas of the brain doing many different things. So anything that exists in that global average of the whole brain can't be neural activity because the brain doesn't function that way. So it must be dominated by all these noise sources, respiration and cardiac and other stuff. And there's good evidence to back that up in that if you look at that global signal, you're going to see the respiration signal. You're going to see, some evidence of a cardiac signal. You're going to see some evidence of motion. So that stuff's all in there. So the idea is by regressing that out, it's dominated by those noise sources, and everything out left is the true signal of the brain. But it gets a little bit more complex than that because when you remove the global signal, you're actually doing a mathematical function. So the easiest, regardless of the data source, the easiest way of thinking of this is, let's say you have two time series that have no relationship to each other at all. And you average them together, and you remove that average from those two time series. what you have left is essentially anything that was randomly in common in those 2 time series is removed. Therefore, those 2 time series, anything that's left is the exact opposite. So you essentially create 2 time series that are perfectly opposite by removing what's common between the two. So that's kind of like the simplest example. But if you think about it on, instead of just 2 time series, 10,000 time series, what you end up doing is, no matter your system, if you remove the average, you're causing things to become anti-correlated or opposite each other in every situation. So if you, instead of running this analysis where we get these 2 anti-correlated networks with global regression, if we use other noise removal methods, you still see that default mode network, but you don't reliably see those anti-correlated networks anymore. And I think the key point here is it's not just this mathematical. So for a while, the response was, okay, yeah, so it causes anti-correlated networks, so we're not going to sort of think too heavily on whether, these two regions of the brain are correlated or anti-correlated. We're just going to say they're different and they're different networks. And as long as we're focusing on that, we don't have a problem. We can still use this method. It still removes a lot of noise. It absolutely does remove a lot of noise. But we don't, as long as we just don't try and overinterpret what's, bigger and smaller, or positive or correlated, anti-correlated, we're still good. The trouble with that is the global signal isn't, like I said, it does have all these noise sources in it, but it has other stuff too. There's been studies showing that if you look at the properties of that global signal, it varies depending on whether people have schizophrenia. It varies, so that's the first paper here. The second paper shows that the global signal includes a link to EEG signal fluctuations relating to attention. This third one shows that, if you're removing it, it's going to skew the results you get in a study comparing autism spectrum autistic volunteers from other kids. And it even varies on caffeine. So if you do you take a drug that's global alertness, like caffeine, that causes vasoconstriction across the whole brain, and surprise, surprise, you are altering the global signal in a potentially neural way. So the method has severe limitations if you're trying to compare across populations. And one of my general recommendations every time I see someone using global signal across populations isn't don't use it, it's do a group analysis, correlate the global signal to each of your populations separately, and if you see a population effect based on how your global signal correlates to the brain, you have a problem. And interestingly, most people have suggested is to end up not using global signal, but it's a good test if it is a valuable method for you. Is that a hand in the back or just resting? Okay, never mind. So before I get too negative on this, I think I want to get back to my original point of the methods we use for denoising really depend on what our goals are. So if you're trying to do these correlation-based population differences, global signal, I think, is extremely problematic in a lot of situations. But let's say you're not using global signal to do a population difference. You're just trying to use it as a normalization tool. So here's a study. This is going to be a little bit tricky because a lot of you, I don't think we've done a lecture with connectivity analyses in this series yet. So this might be a little bit confusing to some of you, but hopefully it'll make sense in future lectures. So one way of visualizing data is we divide the brain into a bunch of regions of interest. And each region of interest is sort of a line here. And we can correlate each region of interest to every other region of interest. And you get this, what's called a connectivity matrix of all these regions of interest. And that matrix is going to sort of vary based on the baseline correlation of everything. But what we could do is we could just say, whatever this matrix is, we just want to sort of center it. So we can set the mean of it to 0 and the standard deviation of it is to 1, and that's what we get here. Or we can do that same normalization another way, which is before we do the correlations, we're going to regress out the global signal, and then this matrix from a single subject will look different, but these matrices between subjects are going to be normalized in a way that makes them more similar to each other. So in this case, we're less concerned with what's bigger and what's smaller. across populations, we're concerned about the pattern. And the reason this comes in relevant is in this specific study, it was the data I'm showing here was a poster at last year's a conference from last summer, but there's also been a similar observation in a recent preprint, which says that if we look at these correlation matrices across the population, the patterns that we see here are predictive of an intelligence score. And in this case, this is an external measure, and there's predictability. But what we could see is if we use these original matrices, the blue lines, on a bunch of different data sets, it's predictive but kind of weak. If we normalize it to sort of scale out the individual, this baseline shift between subjects, it gets a lot stronger. And if we do global regression, it gets a lot stronger. So here, global regression is not just a denoising tool. It's a relative normalization tool across the population, and that seems to highlight one of the a relevant behavioral measure in these data sets. The one thing I'll note here is the global signal does do better than normalization, but I'm not sure if that's because it is actually a superior method or because in this specific data set, we're not actually doing any other type of noise removal. So if we potentially remove that cardiac and respiratory signal and then did normalization, it might have given this better too. So it's just a helpful note that the different methods used to noise do interact with our analysis method choices. So just to sort of sum up this specific case study on global signal, I think just a big take-home method for all the methods here, and I don't want to just sort of pick on global signal alone, is if we remove some of the data without examining what it is or isn't, it can have unanticipated consequences. I should say that there's probably 5 to 10 years of fMRI papers that do global signal regression that the field as a whole probably doesn't really know what to do with right now because of these issues. And if it was sort of examined more at the beginning, we could have probably gotten more of the field on a healthier footing earlier. And it's, on a fundamental level, the original goal was to make these between brain region comparisons cleaner with less noise. And those are the exact type of connections that global signal regression makes it the hardest to interpret. But like I said, it doesn't mean, it depends on what you're using it for. So there's a chance that if we're using it for other measures, it might be a powerful tool for this type of stuff. But I think there's more work to do on there before we sort of say any one method is the best. Or to go back to my title, there's no method that's the best, it's the least worst methods. So I'm still continuing in this section on removing what we think is noise. But before I go into the next section, any question? Okay. So one big category which I would put in this general philosophy of removing what we think is noise is ICA-based analyses. So ICA is I guess a mathematical algorithm. I don't know a better way to sort of describe it, but that takes your data. So let's say we take our brain data and we divide it, instead of having it 3D brain volumes over time, we turn it into a two-dimensional matrix, where every voxel in the brain is one dimension of this matrix, and every time point is another dimension. What ICA does is it divides this into two matrices that can be multiplied with each other. One matrix is these time courses by what are called independent component analyses, so by components. And the other matrix is components across space. And what you can look at these time series, and for each component we get a time course, and we also get a map of weights across space. And in this case, this is called spatial ICA. Each of these is going to be independent of each other. So if you multiply them together, there's going to be no overlap. It's hard to know what terminology to use here because I know the mathematical background in this room varies widely. And the reason this method is useful is because it takes sort of this mush of data and it divides the data into these components that theoretically have independent and interesting properties. So one of the early papers that used ICA for fMRI data looked at these ICA components and said some of these components match up with pathways that we know exist in the brain. So in this case, they identified 5 networks. And it's important to note that they assign these names, but based on my theme here of removing noise what we think is noise, these names aren't from the data. These names are, they looked at this and said, we know this is early visual cortex. We know these are the areas that are involved in identifying what objects someone are. So they're assigning labels to these based on other knowledge of what we think, how we think the brain functions. And the way ICA is used in a denoising framework is you can take your data set, you do this ICA, you get these components with time series and spatial maps, and you divide them into components that we call signal and components that we call noise. And this could be done either manually, just looking at them by eye. It can be done semi-automated, something that says these are the ones likely noise and likely not noise, take a look yourself. Or it could be fully automated where an algorithm just pops out, keep these, get rid of these. And then once you get those clean ones, there's other cleaning steps you can add, and you end up with a data set without noise. I should note I took this picture from a presentation that was given at an educational series a couple years ago at the OHBM meeting. This entire talk is available online. I'm going to borrow from this talk and Dr. Grafanti's talk and a couple other talks during this lecture, but you can actually view all these online. This slide will also be online, so if you don't want to frantically write down long web addresses on any of these slides, you can find these later. So what do these components look like when you're talking about noise removal? So this is a paper that Dr. Grafanti published that was kind of a basis for that talk, where we look at this one component. This is an example of a spatial map. So the gray area is just the background image, and the color area is the ICA weight, spatial weight for that component. And what we could see is just looking at this, you could see that the brightest areas are on the edge of the brain. We can look at the time series of that component. And what we see here is that the signal is moving along happily, and then it has a drop, essentially 100% signal drop. So it's dropping down essentially an order of magnitude beyond what the signal looks like, and then it returns to baseline. And if you look at the motion alignment parameters, you see that there's a bounce in motion right around that point. So you could say, this component seems to be heavily weighted towards head motion. It's noise. Let's get rid of it. Here's another component where you can see it's really heavily weighted in kind of this back area, but if you look at the sagittal area of the brain, it's a really bright weighting right along the middle of the brain. And being the ICA component identification expert we all are, we could say, that kind of looks like where the sagittal sinus, kind of a big draining vein, is going to be. And we look at the time series, it kind of looks normal. But if you look at the frequency of this time series, what we see is kind of a lot additional signal at these high frequency areas, which are more affiliated with respiration and cardiac signal. So we could say, this is probably a respiratory artifact or cardiac artifact. Let's remove that one. We can take another signal and say, this kind of looks like that resting state default mode network we were talking about earlier. It's more in the brain, it's more in the cortex. I don't see anything jumping out as weird in this time series. I'll finish the slide, then I'll answer the question. And most of the information is low frequency. I think this is a good signal, and I'm going to keep it. Yes?
So back a few slides to the chart.
Yeah?
What is the difference there between the non-aggressive and aggressive?
I actually, as I was looking at it right now, I forget exactly what Dr. Grafanti was referring to there, but after you do this ICA component selection, you can do other denoising steps as well. So, I guess there's two ways of saying it. When you're making the component selection, you could be aggressive in saying things are noise, like essentially anything that you think might be noise, you remove, or you could say anything you're not sure of, you keep. So I know that's sometimes how aggressive and non-aggressive is used. It could also be used saying, additional noise processing steps afterwards. Jason, do you have another addition? Uh-huh.
Regress, more aggressive you regress out the noise before you do the
Okay. So Jason Avery was also saying that it might that the other way people do it is when do you just directly regress out the noise components from the original data, or do you combine everything in one model and regress out, just part of it based on a large model, which would be a little bit, essentially what that would mean is any shared information between the noise and non-noise signals, because I guess one way of saying this is this is spatial ICA. So the components are independent in space, but not time. So there's times. So the time series actually can share information. So if there's shared information between time series that is being kept and removed, the question is, do you want to keep that shared information or remove it? So if you're going to be aggressive, you're going to remove any shared information, and if you're going to be a little bit less aggressive, you want to keep that shared information. Thank you for bringing that up. That was a important, good point to add. So I just kind of showed you 3 components here of how you can just sort of look at it by eye and say what to keep or remove. There are a bunch of algorithms that try and do this automatically. So I'm not going to go into like how these exist and how they differ, but I think some of the common ones being used nowadays are Fix and Aroma. And the basic question here is, what features of the data do they use to decide what's signal and noise? How aggressive they are? Are they trying to remove certain types of noise? And do you have to train them on specific, on a bunch of data from your data set, or are they supposed to sort of work out of the box on any data set? The other thing I'll add, in addition to Dr. Griffanti's slide, is there has been some additional work that fits into this using, instead of spatial ICA, temporal ICA. And the current approach is kind of a hybrid because it both uses temporal ICA and this fixed spatial ICA in kind of this Frankensteinish but potentially useful combination to do it. And it's worth knowing this exists, and there's a lot of potential with that method, but I'm not going to sort of break down these methods in this talk today. But it's good to know it's out there. To sum up this section on removing what we think is noise, I think one of the biggest pluses is you can use these methods on pretty much any fMRI data because they don't depend on anything besides the data. And that makes them really convenient. They've been repeatedly shown to be useful, and they can be automated. So like in my theme of the least bad methods, these methods do work. They do make your data cleaner. And people like to use them. But with all these methods, I kind of highlighted it with the global signal, but it's true with the ICA methods too. There's nothing magical about ICA that says ICA components are going to be pure, every ICA component is going to be a noise component or a signal component. There's nothing about ICA that says that's going to happen. It just seems to mostly happen. So whenever you're removing an ICA component, it's almost definite you're removing some things you don't want to remove. And whenever you keep an ICA component, it's almost definitely you're keeping some things that you wish you didn't remove. So there's nothing, in all these methods, even ICA, they're not going to be perfect noise removal methods. And depending which methods you use, if you don't know or don't try and figure out what you're losing in the process, you risk sort of your ability to interpret the results. And that varies very much on study goals and study outcomes. So I'm not saying that's specific to any of these methods, but it's really depending on your scenario and your situation. So I'm going to jump into the next section now. Does anyone have any questions before I do that? Okay. So the next philosophy of noise removal is what I call reduction based on external measures of noise sources. And the big category of this is what I'm going to call nuisance regressors. So what that means is you take some sort of external measure, you either cardiac signal, respiration signal, head motion signal, and you regress this out from the data. And I'm also realizing I'm using the word regression here a lot, which I suspect many, but not everyone in this room knows what it means. So just as sort of a basic level, what regression essentially means is you take 2 time series and you fit one time series together. So you scale it and shift it so that they match as close as possible. And when I'm talking about regressing out, you make that fit in some way, and then you remove anything that fits. So back on that example of the linear drift, you take a line with a slope, you fit your data to that line with a slope as best as you can, and then you remove everything that matches the fit, so you're left essentially with data that has everything but that slope in it. And to continue my theme that these are philosophies, not hard rules on how we do data analysis, these all are, the idea of these external measures is you're moving something more grounded in what you know is noise. So we know that, for the most part, when you're taking a deep breath, that's not your brain response. So anything that correlates to deep breath is something that we very likely want to remove. We know when you move your head, that's not the signal we want. So we know we can remove that stuff and regress it out. So that's kind of the core of this philosophy. But in practice, the way we get these measures can be data-based. So we can use external measures of cardiac, of your pulse and respiration, or we can look in the data and say, that big draining vein sagittal sinus, that contains the information of pulse and respiration, we can use it. There's new approaches with machine learning tools that also do that as well. So, kind of to model this respiration issue on actual data instead of my simulation at the beginning. If we take either task data or an area with task or an area without task, we have the raw signal in black. We have the task signal in blue. So that's if we fit our task model to data, we get that blue curve. And we have the task signal is what we expect the signal to look like, and the red signal is the fit. And if we look at this at the time series and we look at the frequency, so in these plots of power spectrum, these are low frequency signals, so things that are, events that are happening slower, they're cycling on and off slower than once every 10 seconds. And here's an event that's cycling on and off about once every second. So if we look at this frequency on high resolution data, what we see is a peak at around 1 second, which is your pulsation, because your heart beats about 60 beats a minute. And you sometimes see a little bump lower down. And our task, which is slower than 10 seconds, is mostly happening at these low frequencies. One thing worth noting is if you're not sampling fast enough to get those 1 second signals, sometimes these respiration and cardiac signals can fold over back into the data, which is explaining why is a bit beyond the scope of this talk, but it's one of the reasons why these signals are hard to remove. You can't just sort of say, let me get rid of the high frequency data if you're collecting data only once every 2 seconds. Or you can't get rid of data that's happening every second when you're only collecting a volume every 2 seconds. So when we're talking about this pulse and respiration, let's say these are each volume we're getting. We can also get the pulse oximeter traces. So this is the pulse using an optical measure of the finger. And we can get the respiration trace on how much the chest breathes in and out. I should note, by the way, these slides are all from another talk in that same series from a conference 2 years ago, and this is that same link. So the original method that used these is a method called retroICOR from back in 2000. And it takes these signals, it essentially models how we expect those signals will affect the fMRI signal using a bunch of sines and cosines, and it actively removes them from the data set. And when you remove them, what you could see is if before removal, we get a high peak for respiration at around a breath every 5 to 6 seconds, and you get a peak a little, this looks like someone whose heart is beating 40 beats a minute or 50 beats a minute. But after you do this retroICOR analysis, those peaks drop out. So the idea is you're not removing this based on what's in the data. You have this other measure that says this is what we expect cardiac and respiration to look like, and we can actively remove them based on the information we have. Since this method, there's been a bunch of other people trying to find other signals in these data that we can regress out. So some other work that was done here at NIH is what used a measure called respiration volume over time, where you take this respiration trace, you look at the envelope of that trace. So essentially, the peaks and troughs of your breathing cycle. And you can say, there's something about how this computer is set up when I touch the trackpad, it advances slides. And what you could say is sometimes, so the areas where this is bigger, people are taking deeper breaths. And the areas when it's shallower, narrower, are when people are taking shallower breaths. So if you want to think of this from what we're seeing in the MRI signal, when you're taking deeper, slower breaths, you're getting more oxygen in each breath, and that oxygen is sort of staying in your system longer versus shallow breaths where you might be inhaling a little bit less oxygen and exhaling a little bit less CO2 per breath. So that's the model for why this would affect the fMRI signal. And the important thing for this is, unlike the other method, retro-ICOR, this is actually going to be a bold-weighted signal. So it's going to, because it's based on how much oxygen is in your blood. So this paper, which I'm not citing here, it's Rasmus Bern et al., 2007, showed that you can regress this out from the data and improve data quality from this method as well. And the key here is, again, getting back to the issue of sort of regressing out without knowledge. If I look at the respiration changes for, of this volume over time, and you correlate to the brain, this is what we see. If we look at that default mode network from the same seed, we see a fairly similar map of regions. And the reason for that is twofold. One is because if you're not regressing out the signal, it's going to bias whatever you look at for your seed. Number two, it turns out that this default mode network actually happens to be slightly more vascularized than other areas of the brain. So any signal that's pulsing respiration is going to bias itself a little bit more towards this default mode network than other areas. So this has been shown in a few different studies, but it's one of the cautions of trying to do connectivity analyses without trying to account for respiration and cardiac signal. The other there's several intermediate methods for external validation. The one I want to focus on here is it is using an external measure, but it's using it from only within the data set. And I don't expect everyone to understand this anti-core method perfectly based on one slide, but I'm presenting it mainly to give a sense for the ways people think about noise removal. The basic idea here is, if you look at the brain, we think most of our signal is going to be in the gray matter. Less of our bold signal changes is going to be in the white matter. But if we take sort of a white matter wide signal, there's going to be something in there that we don't want. But if we say signal that appears in this gray matter, but not, essentially signal that appears in both neighboring gray and white matter is more likely to be artifact than signal that appears just in the gray matter. So it essentially takes this that's called the spotlight, and it moves it around, and there's a strict criteria for voxels that are only white matter, and it says for anywhere in the spotlight, take the voxels that are just white matter and regress it only from the gray matter voxels in sort of a similar spotlight area. And what that does is it's particularly sensitive to scanner artifacts in how it removes signal, but it's sort of a principled way to do sort of this nuisance regression, but it's still based on some sort of external validation of what we're measuring. Again, like the first methods, we're making assumptions about what is or isn't noise here, but it is sort of rooted a little bit more in the data. So it's kind of a hybrid method between the first two philosophies I brought up in this talk. To finish up this section, actually, minus one slide, with these nuisance regression approaches, the key obviously is they're based on some external measure, which is less likely to be biased than if you're using stuff in the data. They clearly can remove much of the noise. There's been a lot of studies to show this. But a key thing that I've sort of glanced on here is they're only good as the model. So like the retro-ICOR model, the RVT model, all these different approaches, there's an assumption of how to take your cardiac signal and respiration signal and best regress out noise in the data. And those assumptions are good, but I'm positive they're not perfect. The extreme example is breath hold has a very distinct response that we don't want. And if people hold their breath, none of these methods are going to account for that signal correctly. And the last thing I want to bring up as another word of caution is all these nuisance regression approaches have to fit in some sort of more complex processing pipeline, and where they fit in can be tricky. This review article from 2017 is a good place to sort of get more information from that. And a lot of a general overview of these methods and others is in this review paper also from 2017. Any questions so far? Okay. Another just single slide I want to bring up because this is a method that isn't often talked about as a noise removal method, but I think actually is. There's a fairly new analysis called intersubject correlation. I'd say it. The first papers were about 5 years ago or so. Maybe the originals are a little bit older. And the basic idea is you take a bunch of individuals, you show them the exact same stimulus at different times. So typically, let's say you show them a Hollywood movie. And you say, instead of correlating within an individual's brain, you say, take every location of the brain, you align the brains to each other, and you say, what areas of the brain is the signal going up and down at the same time in these separate individuals? And the idea is areas where the brains are doing the same thing at different times in different people are likely to be neural. And we mostly think about this as sort of the common shared neural signal across subjects. And there's a lot of ways to use this design, but it is actually a noise removal technique, because what we're actually saying is anything that isn't common across subjects for this analysis approach, we're assuming is noise. And right now it's been mostly used for natural viewing, but there's potential to sort of think about it, as a noise removal technique more widely, of trying to remove shared or unshared fluctuations over time. I'm seeing a few quizzical eyes. I can talk more about this afterwards. I do want to get through the last section. So the last section is noise removal based on physical properties of the data. There's a large category that I'm not covering in this talk, which is trying to use some sort of external MRI scans to remove noise. So for example, we know that a lot of signal distortions are coming from what's called field inhomogeneities in the scanner. So if we measure those field inhomogeneities, we can empirically correct some of those distortions. And there's a large class of distortion corrections and signal corrections where you collect some sort of extra scan beyond fMRI and use that information to improve your data. There can and may be an entire lecture on just that topic. I don't think there is this year. There's some lectures in the past years of this series you can see online that cover that stuff a bit more. The other approach I'm not really covering in here is calibration scans, which means you're doing some sort of functional scan. It could either be a baseline task, a breath hold, CO2 breathing, a baseline CBF scan, and you use that information to account for some, the physical information you get from those scans to account for some of the variation in the fMRI scans you care about. And just sort of the one example to get what I'm talking about here in general is multi-echo fMRI. So I could focus on a lot of stuff, but I wanted to just sort of hit one of these methods to give you a sense of what fits into this philosophy of noise removal. So what multi-echo fMRI is typically in fMRI, we collect our data and we collect data with what's called a single echo time. So the echo time is the time between when we excite the protons and we collect data. And the reason it's important is because when we talk about the blood oxygen-weighted signal that we usually care about with fMRI, there's a delay, an echo time, that is optimal given a bunch of scanner parameters for what we want to measure. So if we collect with too short an echo time, we're not going to get as much blood oxygen weighting. And if we collect with too long an echo time, we're not going to get as much blood oxygen weighting. And so normally with single echo, we find that weighting that is the best for bold, and we use just that. So looking at this here, so this is echo time equals 30 in this sort of visualization. And you can see that in this block design task, the responses are biggest when that happens. But if instead of collecting data with one echo, you're collecting in the exact same scan data with multi-echoes. So you excite the protons, you collect one volume, you collect another volume, you collect another volume, you collect another volume, all after that one excitation. You get this series where where some volumes are collected with suboptimal echoes for bold weighting, and some are collected with more optimal echoes of the bold weighting. And what that lets you do is you can now model it. You could say, in this case, this is an ICA-based method for multi-echo denoising. So you can take one of these ICA components. You can say, if this component is bold weighted, we expect the signal to increase as our echoes get longer. If, so that the difference between the baselines and the peaks to increase as the echoes get longer. If the signal is not bold weighted, we expect it to kind of stay the same across all these signals. So in this case, I'm not going to go into all the math here. There's actually a lecture online that goes in, actually, if you go to the summer course from last year, there's a full lecture or two on multi-echo imaging. So if you want to know more, you can look at that lecture from last year. So you can essentially say this component looks fairly bold weighted based on the physical properties of how the signal evolves over echoes. Here's a component that, again, we can just look at it and say that's probably a motion component with the edge. But if you look at how it fits to this model, it actually fits better to a model that's non-bold weighted. And there's no way I can explain this completely in a couple of minutes. So if you do want to learn more, I suggest looking at the next talk, the talk from last year, or speak to me afterwards. But the basic idea here is you can, for every one of these ICA components, you can give it a weight of how bold weighted or non-bold weighted it is. You can sort them based on this ranking and say, the components that, based on the physical properties of the data, are bold weighted, I'm going to call these, and the ones that have much lower bold weighted go here. And if we look at a lot of the components that we're calling bold weighted, they look, they're in the cortex, they look brain networky. And if you look at a bunch of the components that this algorithm automatically, based on the actual physical properties of the data, say aren't bold weighted, they look like artifacts. So we get, again, the motion, we get maybe sagittal sinus, we get dropout signal. So it's a way to empirically separate these methods. And I should note that multi-echo imaging is an area under significant development. This multi-echo ICA method has gotten a lot of attention, but it's not the only method that is or could exist. The reason I'm focusing it is because there is now a trail of publications that show it really does help with remove noise sources with an empirical physical basis in the data. It has the potential to retain difficult non-noise signals. So I actually began this talk with an example of multi-echo denoising, where we kept the linear drift, the slow linear change that was neural, and removed the slow linear change that was not neural. So I think there's almost no other method out there right now that would let you do that. That said, this method still relies on ICA, which still has that assumption that every component is either noise or not noise, and that assumption is good but false. Or some noise signals like respiration are bold weighted. So even if this method works perfectly, it's never going to remove a bold, an artifact that varies with blood oxygenation. And this is still under development. So you can run these analyses now, but I think the ways you can run them are going to look different and hopefully better a couple of years from now than they are now. And the decision process of what is or is not, I like to say it's empirical, but there's still a decision tree with judgment calls on what is or isn't appropriate to remove. And I think the last key point is there are other approaches that use multi-echo fMRI under development. So I think multi-echo itself is extremely exciting. Whether this one algorithm I showed is going to be sort of the approach that is going to last for a long time, I think time will tell. So the last very quick section, I'm pretty much out of time, so I'll just kind of quickly go through this, is I do want to cover this because I think it's an area that a lot of people don't think about that much, is sometimes the best approach to noise reduction is to avoid analyses that are going to cause the problem. So if you have two populations where you know head motion varies, kids and adults, patients certain patients with healthy volunteers, don't use a method that's going to be extremely sensitive to that head motion. So if you're talking about like a global functional activity measure, that might be particularly sensitive to that. Similarly, if you're comparing populations with neurovascular coupling methods, use caution if the methods is going to be oversensitive to that. So if you're doing a task fMRI, avoid a method that's going to be really sensitive to, if you get 1% or 1.5% signal change. And these are sort of general statements, but there's a bunch of approaches that have developed in this area. So there's an approach that's a while ago called N-pairs, which is essentially create multiple analysis pipelines, make a validation on whether these analysis pipelines are doing what they're supposed to, an independent validation, and compare them to each other. So this method's from 2012. A kind of review of these methods from the same group was published a couple of years ago. There's other pipeline tools that I think are going to get more and more used for this sort of way of thinking about data. So NePipe is something that's currently under development as sort of a pipeline comparison tool. And this paper actually, preprint came out like 2 days ago, and it's purportedly showing that when we're talking about task fMRI in large populations, these task measures are really inconsistent across populations. And that's kind of the message coming from that paper. I think my first read of the paper, I think it's being a little bit too negative. I think they've actually done a real service to the field, and they're developing a framework for saying what is good and what is bad, but they're focusing on essentially one data set and one pre-processing pipeline. They're focusing on 2 data sets and one pre-processing pipeline for each of those 2 data sets. So it's a framework for thinking about what methods are more and less robust to noise in ways we care about. And I'm excited to see how that goes forward, even if I think sort of the take-home message might be a little bit more negative than necessary. And just at the final end, through this talk, you'll notice that I've been quoting a talk series and a lot of papers from 2017. That's because there was a special issue of Neuroimage that is all about noise removal from 2017, and I borrowed widely from there. And paired with that, there was an educational symposium that included some authors of the papers in that series. So if you want to sort of get a sense of what's in the literature, those papers and reviews and that talk series are a good place to go. So that's about it. Any questions? Okay. Feel free to ask questions afterwards as well. Thank you.